So I hope you can see the presentation on the screen. I hope you can see the presentation on the screen. I don't know if Moses is not there. And you're so few today, you're only 29.
Yes.
Mirago, you can see it?
Yes.
Okay, so let's continue. So in the last class, if you just to go through very quickly, we said a typical regulated power supply. This left-hand side is the input, the right-hand side is the input, is the output. So you need a component similar to this one with a resistor and a zener. This will be called our reference circuit. You need an amplifier, which we call our error amplifier. You need a sampling circuit to sample the output voltage so that you can compare it with the reference signal. So you need a sampling circuit, and a simple sampling circuit is just to use two resistors. So that, for example, in this case, the sample voltage will be R2 divided by R1 plus R2 into V0. And then you need a control element. So further, we say that the control element can be in series, like in this configuration, the control element can be in series, or this control element means in series with the input voltage and the load, or the control element can be in shunt with the load. So in case this is in series, we call it a series regulator. If it is in shunt, we call it a shunt regulator. And then we have a special type of control element which just behaves like a switch. It turns on and off. So in this case, it will be called a switch mode power supply. It will be called a switch mode power supply. So basically, those are the circuit elements which are required in a DC regulated power supply. So I described all the functions of the elements. So these are the topologies, just simple topologies. If this is the input voltage, this is your load, and this is your control element. For a linear power supply, the control element just acts like a resistor. It just acts like a resistor. So the load voltage will be given by the input voltage V1 minus the drop across this control element, which is acting as a linear resistor. So V0 will just be V1 minus this series resistance, RS there stands for series resistance, times the load resistance. So we say that the output is linearly related to the control, I could write the control resistance, or you can say the control element resistance of the series element. So this is just a topology. I just simplified topology of what is happening. And then we have the other one, which is called a linear shunt regulator. So here your input voltage is V1 over here. We have a series resistance over here. Then your control element is this variable resistance, which I'm calling RS over here. And then your load is over here. Your load is over here. So there'll be two currents flowing. One will call ISH, which is I shunt, and the other current will be called I load, or a load current. And therefore V0, the output voltage for this case, will be V1, our input voltage, minus the total current, ISH plus IL into R as the output voltage. And a typical circuit of this one, it looks like this one over here. So you have your reference circuit over here at the input. You got your error amplifier over here. And then you got your sample voltage. No, not in this case, the sample voltage goes to the positive part. to the positive input. And normally in exam, I normally ask or CAT to explain the functioning of this circuit. Okay, so you got to know how it works, But the difference, look at this. In this case, the sample voltage goes to the positive of the error amplifier. And in the other one, I don't know if I drew it somewhere. Yeah, in the most of the series ones, the sample voltage goes to the negative. Okay. And that is required for proper operation. So this is a typical circuit of a shunt regulator. So this part over here is your reference circuit. This amplifier is your error amplifier. R1 and R2 are your sampling, output voltage sampling element. And then the transistor over here is your control element. And then you got your load over here. And then the last type of regulator, I've just done a very simple representation over here. I'll not put the feedback in this one, but basically I'm showing that you have your input voltage, then you got a switch over here. This switch is normally controlled by a switching circuit, which compares some reference to the sampled voltage, and therefore it will control the duration, what we call the pulse width, which determines the resultant voltage that appears at the output. Now for this course, this last topic, I normally give it to students because I've been spoon feeding you all along. So you go and study this one and we'll set up some simple problems. So in this case, the switch goes off and on, and this is a flyback diode. Okay, so when the switch is closed, this side of the inductor becomes positive with respect to this one. When the switch is opened, the magnetic field collapses inside the inductor. This side becomes negative and this side becomes positive. So a current, the energy stored in the conductor continues to flow to the output. So sometimes it's called a freewheeling diode. This diode here, sometimes it's called an idling diode, and that is its function. It also protects the switching device so that you don't have a large back EMF going to our switch, our semiconductor. Normally the switch is a semiconductor switch, a MOSFET. Okay, but in this case, we control the voltage by the duration in which the switch is on. With respect to the time period of the switching. So we can get an equation that V naught is T on divided by T on plus T off into V1. So these are the typical topologies. Of course, I've really simplified like this one with the switching circuit, the switching topology of a regulated power supply. I have not put the feedback and all this, the feedback circuit. Yes? Who was that asking a question? Okay, so we'll continue. So for your assignment, you'll do the simple problems. I've already give you the references. The best book for this section is called Professor Sen, Power Electronics by Professor Sen. I don't know if I'm sure you'll get it in the internet. I don't even if I've uploaded it to you people, but it's the best book for power electronics for this particular section. So what I want to do, so basically we're going to study 3 regulators, starting with the series regulator, shunt regulator. Then for your assignment, you will do switching regulators. Switching regulators. Now I want to start with the shunt regulators because whenever I ask questions on the shunt regulators, no student ever answers it. Series regulator is very simple. I also managed to get for you a typical computer power supply. For those of you who've not seen, it. Let me see if I can get it before we come back to the class notes. No, let me go to the class notes. Then if we get time, we'll do it. Now, the designs of all these practical regulators, the simplest is the series regulator. Even the analysis is the simplest. Shunt regulator, the analysis is a bit involved. That's why I want to do it first. Because whenever I set a question, students do not answer. Students do not answer. So this is a typical circuit of a shunt regulator. So it's called shunt because the control element, which is this transistor over here, is in shunt with this unregulated supply. So the unregulated supply is on the left, and the load, which is on the right. Okay, so let's analyze such a circuit. And before even we go there, let's see how does it work. How does this regulator works? So let's assume the output voltage was something, maybe the desired voltage. Somebody wants to come in and I can't see him. Let's help him. Phineas Mugambi. Now, if you're a friend of Phineas Mugambi, please tell him he's disturbing the class. So let's assume that the output was as prescribed. We can take maybe an arbitrary voltage, say 10 volts. Let's assume it was 10 volts. And then we increase the load. If we increase the load, what's going to happen? This output voltage is going to drop. Okay, it might drop maybe to, let's assume hypothetically, it drops to 9 volts because we increase the load. And if you increase if it drops, then it means that the voltage to the positive, remember, in this circuit, let me just magnify it a bit. So for example, so let's assume V0 was your correct design voltage. The voltage at this point will be, and the voltage at this point over here will be beta V0, where beta is equal to R2, R1 plus R2 into V0. So this is your reference voltage from your Zener. We normally call it Vref. And therefore, if I call the output of my op amp V naught dash, say. Let's not call it V naught. Let's just call it V dash, because V naught is that. Let's just call it V dash. So V dash in general, if I just write it at the bottom here, V dash will be equal to beta V naught minus V ref all into the difference gain of your op-amp. So when the load increases, when the load increases, beta V naught will fall. So this term over here, beta V naught will fall. Somebody else wants to come in again. I don't know why you students are like this. Or we can even just look at it from the diagram. For an op-amp, since the ref is fixed, if the voltage at the positive goes down, the voltage at the output will also go down. And therefore, the drive of this transistor at the output will go down. And therefore, the current, which we normally call ISH, will decrease. It will fall down. And therefore, more current is going to go to the load. More current is going to go to the load. So that is how this system works. If on the other hand there was a heavy load, and you remove the load, so if you remove the load, the voltage will tend to shoot up. So if I consider case 2, I'll draw it in blue. So if there's a load at the output and then you decrease the load, so the voltage will tend to shoot up at the output. That means the beta V naught, instead of going down, it will tend to shoot up. And since this increase is connected to the positive, the output voltage is in the same direction, will also tend to shoot up. And when the output voltage shoots up, the drive current of our transistor is going to increase. And when the drive current of our transistor increases, and I think I made a mistake in the first one. I'll just go back to it. When the drive current increases, it means ISH is going to increase. So that's something I think I made a mistake in the first one. So in this case, ISH is going to increase. And therefore, the drop across R is going to be more, and that's going to lower the voltage. So let's start the other one again. I think I made a mistake in the first case, which I've written in pink over here. Let me just rub this. So in case 1, we're considering a case whereby we increase the load. So when you increase the load, if the voltage of something, say V naught, the output voltage will tend to decrease. And when it decreases, the fraction beta V naught so the fraction beta V naught, because of the loading, it will decrease. Okay, so that's why I put this arrow over here. This pointing down means it's decreasing. And since this is connected to the positive of the op amp, it means the output will also decrease, as shown in pink. And when the drive voltage decreases the current, and the drive voltage decreases, the current should also decrease. The current to the collector. And since I need some help over here. Sorry. Let's start again. Output voltage increases. V naught decreases. The fraction of beta V naught decreases. And then it means the output should also decrease. When the output of the op amp decreases, it means the drive to the transistor decreases, and therefore the collector current should decrease, or ISS should decrease, to allow more current to go to the load. Okay, now let's go again and check the other one, which is in blue. So in this case, now the load voltage was something V naught, and then we decrease the load. When you decrease the load, the output voltage will tend to increase. So in this case now, beta V naught will tend to increase. And since it's connected to the positive, this positive input will increase, and therefore the positive output should increase, and therefore the drive voltage to the base of the transistor should increase, and ISH is increasing. Yeah, okay. So ISH now is increasing. If you increase the drive voltage, then ISH is going to increase. This is not the correct blue. So these arrows. Okay, so blue is for load decreasing. So that is how this circuit works. So we'll do it in the proper analysis. We'll do it with the proper analysis and show mathematically what is happening over here. Okay, so the important thing in this case is that the control element, in this case, this transistor, is in shunt with the supply and the load. Now let's see how this circuit works. Let's analyze this circuit and see how it works. So I've got some typed notes over here. We'll go through it slow by slow. Now you want to get this in any book. So this is the same circuit over here. The same circuit we just analyzed. So V1 is our unregulated input. And maybe ask Moses or your CRs. I don't know if I've posted this in your classroom. So if you're a friend of Moses or the ladies here, go and check in the notes that I posted. If it's not there, I'll repost it. So this is the same circuit we just seen. So there's the current I1, which is used to bias our Zener diode. And Vz is the voltage of our Zener. This is our error amplifier. And the output, I'm calling it V naught dash in this case. We've got a second current, which is used to form the sampling network comprising of R1 and R2. So you can see this directly connected to the output. Directly connected to the output. I don't know, I've not written V naught here. So V naught is our output voltage. This is our control element transistor. The current flowing through it is called ISH or I shunt. And then we've got a load current, I've written V naught is here. We've got the current which is going to our load, which I'm calling IL, and this is our load resistor. So this is a simple implementation of a shunt regulator. Shunt regulators, by the way, are not very common because they got very poor efficiency, as we shall see later on. So let's show that this circuit can regulate. And let's find out what is the regulated output voltage. Let's find out what is the regulated output voltage. So we'll start by considering, let's consider the output voltage V naught dash. Let's consider this output voltage V naught dash over here. So V naught dash will be the voltage connected to the positive side minus the voltage connected to the negative side of the op-amp into the difference gain of the op-amp. So we can write that V naught dash is beta V naught minus Vz into AD, where beta is the ratio. It's actually our output sampling ratio, which is R2 over R1 times R2. So beta V naught gives us the voltage that goes to the positive side. Next, we can find out what IB is. IB can be written as V naught dash divided by HIE, because this op-amp sees the input impedance of this transistor, which is HIE. I hope you know from your electronics for transistor, HIE is 25 over IE into milliamps into HFE. For us at present, it's not necessary. Let's just call it HIE. That's the input resistance seen by the op-amp. So if the input voltage is V naught dash, then IB, the current will be the input resistance, it will be V naught dash divided by the input resistance, which is HIE. So that's how I get IB over here. Now I'll just rearrange IB using equation 1 instead of V naught dash. From equation 1 over here, V naught dash is beta V naught minus Vz into AD. So I'll just put it over here. Beta V naught minus Vz into AD over HIE. So that is the current IB, the current going to the base of our transistor. Okay. Now the shunt current of our control element, I shunt, for a transistor, which is our collector current, is just IB into HFE. Okay, or I don't want to use beta because it will confuse us now because we've got two betas. So let's just use HFE, which is the small signal parameter for the current DC current gain over transistor. Not DC current gain, dynamic current gain over transistor. Sorry. So this is IB, and therefore the collector current, I shunt, is just IB into HFE. Remember, this is the collector current of this transistor over here. It's just the collector current. Current is just the gain of the transistor the net. Okay, the network seems to have come back. Odwar Gilbert Davis Albert, yeah, that was disturbing us. Eh? Please switch off your mic, Odwar Davis. Moses, are you there today? I don't want to waste time looking for you. Moses, are you there? Okay, the lady's here. Who is the lady's here?
I'm here.
Ladies. Okay, so yeah, Rebecca, so you leave your mic on. If you see any problems with the network, just talk to me. Huh?
I'm Stephen.
What did you say?
I'm not Rebecca.
Oh, yes. Oh, you're Stephen. Okay. Just leave your mic on. If there's a problem with the network, just speak to me through the mic. Don't write a message because I use full screen presentation. So I won't be able to see it. Okay. So to get the shunt collector current of this transistor, collector current is just times the gain transistor, which I believe is HF. So this is our equation 4 over here. So shunt current is base current times HFE. So it's equation 3, which is our base current. So to get beta V naught minus VZ AD over HIE into. Now let's get V naught. In our circuit, if you look at our circuit over here, I don't know why the speed is so slow now. What's happened? If the input is V1, and with this design resistor R, then V naught is just V1 minus they drop across this R. They drop across this resistance capital R here. And the drop across this resistor is given by R into I2 ISH plus IL. Okay, so that's how we determine V0 from V1. So that's how I get this equation over here, equation 6. So V0 is V1 minus R into I2 plus ISH plus IL. Now let's find out the value of I2, ISH, and IL in terms of the circuit. Now ISH, equation 5 here, equation 5. I don't know, my student computer is responding very slowly. I hope it's not the same with you people. So ISH is equation 5. So this is the middle term in equation 6, ISH. And it's this term over here in 7. I2, IL. So let's go back to the circuit to determine I2 and IL. So this is the circuit. So I2 is a current that passes through R1 and R2. So I2 is just V0 divided by R1 and R plus R2. And IL is just V0 divided by RL. So we can put that in this equation for the output. So from equation 7, I've substituted for I2 in 6. I've also substituted for IL 6. And from 5, we got ISH. So we can write V0 equal to V1. V1 is on voltage minus the brackets R plus R2 plus square bracket V0 minus V over HIE into HFE. That's equation 5 for plus IL, which is just V0 by RL. This expression for V0. So what I've done, let me see if I can bring back a bit of the earlier one, equation 7. So what I've done to go from 7 to 8, multiply the capital R, the minus capital R in the brackets. So the first term after V1 will be this term over here, minus R V0, R1 plus R2. The second term, you multiply all this by minus R, and you'll get R AD HFE divided by HIE into beta V0 minus VZ. And then the last term, which is V0 divided by RL times minus R, you just get minus R V0 over RL. So that's how we go from equations 7 to 8. So now next, you want to collect the terms with V0 to one side. So from equation 8, all the terms which are negative on the right-hand side, with V naught, we'll put them to the left-hand side. So the first term with V naught on the right-hand side is RV naught over R1 plus R2. So it becomes this term over here. I hope your speeds are not as slow as the speed of my internet computer, because when I'm pointing, it's taking a long time before it reaches. Okay, so that's how I get the term after. Now the other negative, which is simple, is the last term, which is my V naught over RL. So I'll put it second over here. And then this term over here in 8 minus AD HFE over HIE. If you multiply it by beta V naught in the square brackets, it becomes negative. So I can take it to the left-hand side also as positive. Then the second term, minus VZ minus RAD HFE over HIE, that's positive. So I'll take it to the right-hand side. So I'll get it over here. VZ. So come to the lead factor V. So I can make common. So the first term is 1, the second will be R plus R1. The third term will be just divided by, which is this term. Are you able to see my cursor? Are you able to see my cursor here?
Yes.
Able to see my cursor?
Yes.
The delay is so long. Okay. Because I can't sit in my student computer. Okay, so this term, so this second term over here, which is from this term over here on 9, which is in 9, it is RAD into beta V naught. What I've done, beta here is not HFE, is a fraction of our beta is R2 by R1 plus R2. So instead of beta, intention is as R2 divided by plus R2. Now all this should equal to the right-hand side. So the right-hand side remains unchanged. It's just V1 into RAD HFE over HIE into VZ. Now I'll make V naught the subject in 11. So V naught will be the right-hand side of equation 10, all divided by the square brackets on the left-hand side. So we get V naught as 11. So now let's simplify equation 11. So I start by dividing the numerator and denominator by R. So the first term in the numerator, if I divide it by R, I'll get V1 divided by R. The second term will just be AD, HFE, HIE into VZ. So that's how we get this term over here. And if I divide the denominator by R, the first term over here will become 1 divided by R. The second term will be, you cancel the R on top over here just remains 1 divided by R plus R2. The third term will just be 1 over RL. The fourth term will just be AD divided by HIE. The fourth term, the 1, 2, 3, 4. So therefore, there are only 4 terms because this one is just a ratio, just multiplied by R2 over R1 plus R2. So all this is just one term. So we get 11. So next, sorry, we get 12. Next, we simplify it further. We divide the equation 12, numerator, denominator by AD. So if you divide the first term in the numerator, which is V1 divided by R, it becomes V1 divided by R into AD, plus the second term, which was AD HFE over HIE into VZ. The AD will cancel, so you just remain with the HFE divided by HIE into VZ. Now let's divide the denominators, terms by AD. So the first term at the bottom, instead of 1 over R, becomes 1 divided by R AD. The second term will become 1 over 1 plus R1 plus R2 into AD. The third term will become 1 over RL into AD. The fourth term will become just HFE over HIE into R2 over R1 plus R2 because it had an AD term. Okay, so now we'll simplify. And now knowing that most op-amps have got a gain of over 100,000, okay, normally because the numbers are so large, in fact, it's much more than 100,000. They're normally given in terms of dB, 80 dB, 100 dB, 110 dB. Okay, so I've just given a value over here. Because 100,000, it will be 20 log 100,000 is how much? 20 log to the base 10 of 10 to the power 1, 2, 3, 4, 5, 10 to the power 5. That's 100 dB. Okay, so let's assume AD is very large, means greater than 100,000. Then all these terms, which have got AD, will be divided by 100,000. So if you start in the numerator, you have V1 over R divided by 100,000. So this term will be negligible. Okay, this term over here will be negligible. Even if V1 is 100 volts divided by 100,000 times R, it will be negligible. So the numerator just remains with HFE divided by HIE into VZ. So that's how we get the numerator of equation 14. Now let's look at the denominator of the right-hand side of 13. So wherever there's an AD, all these terms become so tiny that they can be neglected. So the only term that remains is this term over here, which is HFE over HIE into R2 over R1 plus R2. So if you take those results, you'll get equation 14. Now let's simplify 14. Let's simplify 14. So if you look at the numerator of 14, you got HFE over HIE. And if you look at the denominator of 14, you got HFE over HIE. So these two will cancel. So in the numerator, will just remain with VZ. In the denominator, you'll remain with R2 divided by R1 plus R2. So if you rearrange it, well, you get it in form of this first term of 15, maybe Z over R2 over R1 plus R2. And this is the same as VZ into R1 plus R2 over VZ. Or you can write it as VZ into 1 plus R1 over R2. You just divide this R2 into this other R2 in the numerator in 15, it becomes 1. And so you just remain with this term R1 divided by R2. So you can put the 1 before, then you get Vz to 1 plus R1 over R2. So this is a very important equation. We see that the output voltage of the shunt regulator is just dependent on Vz and R1 and R2. So those are some of the inferences or conclusions you can make. It's not dependent on V1. Remember, V1 is the unregulated input voltage. V1 is the unregulated input voltage. So it tells us if we design our circuit well, the output is not dependent on the input voltage or fluctuations in the input voltage. The output is just dependent on Vz and R1 and R2. Okay, and since R1 and R2 are fixed, once you design it, Vz is also fixed, then the output will not change with fluctuations of the input voltage. Otherwise, it's regulated. So I've given the conclusions over here that from 16, we note the following. V0 is dependent on the values of Vz, R1 and R2. V0 is independent of RL. So if you increase the load or decrease the load, V0 will not change. Okay, because we can't see RL inside the equation 16. So it's only it's independent of RL. It's also the independent of V1, which is our unregulated voltage. Now we can make a lot of other inferences, which I think we'll do it in the next class. Do you have a class after this year?
Yes.
You have a class. Okay, we'll make more inferences in the next class. We'll make more inferences in the next class about this circuit. So we'll stop about there for now and continue in the next class to make some inferences. I decided to go with this one first because students never answer this question whenever it is set. Okay, so thank you, everybody.